This talk is based on the material I present at the biannual Wear of Materials meeting during their Tribology workshop. When modelling wear and failure mechanisms involving lubricated contacts, we are most usually concerned with modelling real systems such as the contacts in mechanisms, gearboxes, engines, bearings, and in machining and forming processes. The special difficulty with lubricated tests is that in a lubricated contact we have a complex system, the performance of which depends not only on the contacting materials, the contact geometry and conditions of load and relative motion, but also on the lubricant additive chemistry. So we are faced simultaneously with issues relating to engineering design, materials and chemistry. A good starting point is to consider those real processes in which we would not expect wear to occur. We can then consider those processes where wear and failure does occur and try to identify the reasons why. Providing we have a clean lubricant free of abrasive particles or wear debris, with a contact operating under fully hydrodynamic or elasto-hydrodynamic conditions, and providing complete separation of the material surfaces, we should not expect to generate any wear. If all types of tribological contact operated with hydrodynamic or elasto-hydrodynamic lubrication, then we would not have any problem with wear. We would need little in terms of lubricant additive chemistry, other than the provision of additives to provide oxidation and shear stability, and we could use any moderately viscous fluid. If this were the case, we could lubricate our systems with glycerine instead of oil. This is clearly not the case. The problem is that in order to generate hydrodynamic separation of the surfaces, any system must fulfill two requirements. Firstly, there must be a mechanism for delivering the lubricant to where it is required and in sufficient quantity to flood the inlet to the contact. Secondly, there must be sufficient entrainment velocity to carry the lubricant into the contact in order for it to generate the necessary hydrodynamic film. This latter condition, except in the case of externally pressurized bearings, requires the contact surfaces to be in motion with at least one surface moving from the direction of lubricant supply and at sufficient speed to generate a thick enough hydrodynamic film. The following sketch illustrates what happens in an elasto-hydrodynamic contact between rollers running with the same surface velocity with a fully flooded inlet. It is important to note that the system is surprisingly very weakly dependent on the load, so once an elasto-hydrodynamic film of sufficient thickness to separate the surfaces is generated, increasing the load has little impact on the level of separation. In an ideal world, we'd like to achieve this kind of lubrication regime, but with many real mechanisms, and more importantly, all mechanisms starting from rest, we are unable to do this. The following shows what happens if the surfaces are sliding in opposite directions. This is the zero entrainment condition. This is what happens when the surfaces are at rest. This is the startup condition. This is what happens when there is insufficient lubricant to flood the inlet. This is what is known as starved lubrication. In the cases where we cannot prevent intimate contact between the mating surfaces, we have to rely on lubricant additive chemistry or coatings to limit wear of the surfaces and to provide protection against scuffing, which is the onset of adhesive wear. It follows that, excluding the special case of rolling contact fatigue, all lubricated wear testing is focused on modelling contacts that are operating outside the hydrodynamic or elasto-hydrodynamic regimes. Under these conditions, lubricant viscosity plays little or no part, and the performance of the contact depends crucially on the lubricant additive chemistry. Examples of such contacts include journal bearings at startup or during starved lubrication because of failure of supply, Elasto-hydrodynamic bearings at startup or during starved lubrication because of failure of supply, piston ring and liner contacts at bottom and top dead center where entrainment velocities fall to zero, piston ring and liner during running because of starved lubrication, gear contacts during running because of negative entrainment, cam and tappet or finger follower contacts during running because of negative entrainment. It is important to note that every time a tribo system goes through a start-stop cycle, or indeed a change of its operating point, there will be a degree of repeat running in. The overall wear of the system is thus the sum of multiple contributions over the lifetime of the components, not simply some constant rate of wear process. As an illustration of the issue of negative entrainment, consider the case of a simple cam and tappet. To generate wear in a lubricated contact, there is no point in choosing a test configuration that produces hydrodynamic separation of the surfaces. Tests must be run under boundary or mixed lubrication. We need to consider the following questions. How much wear do we need to produce? What should the correlation criterion be? How many tests do we need to perform? How do we produce boundary or mixed lubrication regimes, hence wear? And how do we produce wear and not failure? A single wear measurement at the end of the test tells nothing about the wear rate or wear transitions. We therefore need to supplement post-test wear measurements with intelligent real-time observations, of which the most commonly used metric is to use changes in friction, electrical contact potential, and temperature close to the contact zone to indicate possible wear transitions. Hence, in many cases, we do not use real-time wear measurement, but use other methods to identify significant wear transitions. Fired engine tests typically produce no more than about 10 microns of cylinder wear. Wear occurs on both the ring and the liner surface, of course. Even scuffing failure is preceded by mild wear. The deepest honing marks are typically about 10 microns deep and are frequently not fully removed during the engine's life. Thus, the contact is still running on the original surface and is still influenced by the remains of the original surface topography. Hence, to model this, we need to be able to generate and then measure a maximum of approximately 10 microns of wear. Thin, hard coatings are typically 2 to 4 microns thick and do not really wear, but fail through fatigue. Hence, we only really need an online mechanism for detecting that failure. The failure is confined to the coating, and there is no point running on the test once the coating has failed. No one is interested in the frictional wear of the substrate. It's important to ensure that tests run on the coating, not the substrate. Thick coatings are typically 20 to 50 microns thick and do wear. To model this, we need to be able to generate and then measure a maximum of approximately 50 microns of wear, and this is usually confined to the coating. With polymers running against metals, it's possible to generate significant amounts of wear, and once again we potentially need to be able to measure perhaps up to 50 microns of wear. So, how many tests do we need to perform? Wear is a stochastic process. This is obvious with rolling contact fatigue and fretting, but also applies to sliding and sliding rolling contacts. The following example, albeit a dry sliding contact, data courtesy of FIMechE Tribology MV, illustrates the point well. 10 samples each of 3 different polymers were run simultaneously against a steel counterface using a cross-cylinder geometry. This was performed on a 10-station machine. The resulting wear scars were measured and the results presented as box plots. What is of interest here is how the distributions vary significantly depending on the total number of cycles run. This would suggest that, in this case, the number of tests required to achieve an acceptable confidence level may vary depending on the chosen number of cycles. With regard to the question about how many repeat wear tests we need to perform, the answer is that it depends. A box plot allows us to adopt a rational approach to outliers, in other words, measurements that appear to lie an abnormal distance from other values in a series of repeat measurements. A point beyond an inner fence is considered a mild outlier. A point beyond an outer fence is considered an extreme outlier. It will be apparent that if a decision is made to discard extreme outliers, there will be a corresponding improvement in the recalculated confidence level. A sensible sample size for box plots, which is an appropriate method to apply to lubricated sliding wear tests, is perhaps 10 repeat tests. In practice, many experimental tribologists hope to get away with just 3 repeat tests. For tests involving rolling contact fatigue, cycles to failure can be widely different for nominally identical materials running under nominally identical test conditions. This is because the materials are unlikely to be homogeneous, and the fatigue process will be influenced by randomly located stress razors within the core of the material. Whereas it is possible to impose control on what is going on with the surfaces of our sliding wear test samples, we have no way of controlling the subsurface conditions that influence rolling contact fatigue life. Depending on the required confidence level, a minimum of 10, but more usually 20 or 30 repeat tests may be required. In the case of rolling contact fatigue of bearings, it is normal to present results in the form of a Weibull plot. How to produce a boundary or mixed lubrication regime. In order to generate wear, we need to have low surface speeds to ensure boundary or mixed lubrication. We cannot sensibly accelerate our experiments simply by increasing the sliding velocity, because that will change our position on the Strybek curve. Wear tests are likely to take a long time. How to produce wear and not failure. In order to generate wear and not precipitate failure, we need to limit frictional energy input, which requires low sliding speeds. In order to have some control on lubricant additive action, we need to avoid out-of-control frictional heating. We cannot sensibly accelerate our experiments simply by increasing the load. Wear tests are likely to take a long time. Before considering how to model boundary lubricated contacts in a bench test, we need first to concentrate a bit on how lubricant additives work. There are 2 basic forms of additive protection available to surfaces that are either temporarily or permanently in intimate contact: physisorped and chemically reacted. Changes in running conditions or test parameters, for example changing load or frequency of events, will usually cause a temporary change in the consistency of these protective layers or films, indicating some kind of limited dynamic stability. These films may be partially destroyed and reformed each cycle. In other words, each specimen pass may knock the tops off a number of surface asperities, creating new active metal sites. The dwell time between passes allows time for the chemistry to work so that the film, chemical or physical, can reform before the next specimen pass. There is no way, of course, of telling how many asperities could be scraped off in this way, although it must be related to the wear. The rate of formation of the chemically reactive films in particular is considered to be a direct function of the contact temperature. We need temperature to activate and for controlling the rate of reaction, plus a finite time for the chemistry to take effect. The temperature reached at the surface of the contact, the flash temperature, is strongly influenced by the width of the contact, and the flash temperature is responsible for many wear and friction effects. Frictional heating within the contact during relative motion is generated at the asperities, and the resulting flash temperatures can rise to several hundred degrees above the bulk temperature of the surrounding material, but they last for only as long as the individual asperities are in contact. It follows that a very small distance from the asperities, the temperature distribution is smoothed out to give an interfacial bulk temperature from which we can derive an average contact temperature distributed over the nominal contact area. This average contact temperature will always be higher than the bulk temperature of the material, as measured by some sensor embedded in the bulk of the material at some distance from the contacting surfaces. All wear processes are influenced by temperature, be they the formation of oxides on surfaces, the transformation of microstructure, the formation or breakdown of lubricant additive films, or other tribochemical films, or thermal stress-induced failures. To be more specific, wear occurs in conjunction with the dissipation of frictional energy in the contact, and this is always accompanied by a rise in temperature. Different patterns of energy dissipation give rise to different wear mechanisms. The friction power intensity is simply defined as the amount of energy pumped into the rubbing surfaces as they pass through the contact zone. The temperature achieved in the contact and in the bulk material is directly related to the FPI and the size and thermal characteristics of the materials and their supports. The overlap parameter is the ratio of sliding distance for body divided by sliding distance for counterbody. For the thrust washer, this is 1. For fretting tests, it's close to 1, but for pin-on disc tests and the like, it is variable, but is typically less than 0.05. The overlap parameter also applies to reciprocating tests. The longer the stroke, the less the linear wear on the plate sample for a given amount of wear on the moving sample. There are some fundamental problems with the sliding Hertzian point contact test configuration. Firstly, there are no real-life engineering applications that involve sliding Hertzian point contacts. Secondly, tests frequently involve a bearing steel ball sliding against a steel flat. There are few, if any, real engineering applications that involve bearing steel sliding in contact with other steels. If our aim is to model lubricated wear and failure mechanisms in real systems, such as the contacts in mechanisms, gearboxes, engines, bearings, etc., tests involving sliding Hertzian point contacts are not going to provide an adequate model. This is the main reason behind the oft-repeated comment, "I got no correlation between my bench test and the engine test." The most important criterion for correlation between model test and actual application is that the test should reproduce the wear and or failure mechanism of the real application. We really need some common sense here. If the wear generated in the bench test looks nothing like the wear in the real system, the model is wrong. Does any real wear process look like this? If we're interested in wear in real systems, we need to understand something about the wear mechanisms involved in both the real system and the corresponding test model. The following test model example is taken from the 2014 Interlaboratory Tests as per ASTM D7421, standard test method for determining extreme pressure properties of lubricating oils using high-frequency linear oscillating test machine. What mechanisms are contributing to the resulting friction and wear response? What is this test meant to be modelling, and what does it mean? How do we tell the difference between a wear scar and a witness mark? To illustrate this point, consider the sorts of wear scar produced in the HFRR diesel fuel lubricity test. With the low lubricity, that's the bad reference fuel, the main wear scar and the stroke end witness marks merge together into one large wear scar with much less obvious directionality. The wear scar with the low lubricity fluid has the appearance of seizure or galling. This would appear to be an example of junction growth, with the actual area of contact approaching the nominal area of contact. The difference between the wear scars appears primarily to be a difference of wear mechanism, that being for the high lubricity fluid, severe adhesive wear, plus something indeterminate on either side of the wear scar in the direction of motion, and for the low lubricity fluid, seizure. Why bother measuring the scar dimensions? Why not just report whether the fluid produces seizure or not? The conventional method of measuring the wear scar on a ball sample is to measure the wear scar diameter in the direction of sliding and perpendicular to the direction of sliding. But how do we know in a low wear situation that what we are measuring is wear and not simply a sort of witness mark as one would get on a ball in a Brinell hardness test? One approach is to normalize the nominal scar measurement by dividing it by the calculated initial Hertzian contact area. This way we can determine if the measured wear area is larger than the initial Hertzian contact. Although we cannot assume that a normalized wear scar area of 1 indicates no wear, we can assume that a value of 1 indicates a well-performing lubricant compared with a lubricant that produces a value well in excess of 1 for the same test. This approach allows us to determine which lubricants perform well and which ones do not. It is a more rational approach to reporting results than simply relying on an absolute wear scar measurement. In addition to reporting a normalized wear scar measurement, there may also be some benefit in reporting the ellipticity of the wear scar. It must be remembered that as wear takes place, depending on the specimen configuration, the contact area may change and hence the contact pressure. This is particularly the case with the sliding Hertzian point contact. We have long been aware of the fact that in a sliding Hertzian point contact test, the majority of the wear, or plastic deformation, occurs at the very beginning of the test, and that once the difference in wear between candidate samples has been established, the number of cycles over which the test is run is somewhat arbitrary. This example shows what happens if we run the ASTM D6079 diesel fuel lubricity test procedure under the specified load, stroke, temperature and test time, but at different frequencies, hence different number of cycles. Tests were run for 75 minutes each at 5, 10, 20, 30, 40 and 50 Hz, the latter being the standard test frequency. The number of cycles per test was therefore 22,500, 45,000, 90,000, 135,000, 180,000 and 225,000 cycles respectively. 2 repeat tests were performed at each frequency. It is apparent that within approximately 50,000 cycles, the difference in wear between the high and low reference fluids has been established, and that not much changes after that. ASTM D6079 gives a reproducibility figure of 80 microns as the approximate 95% confidence level. It transpires that with the exception of a couple of outliers, tests of 90,000 cycles or more fall within the reproducibility limit. Plotting the average of each pair of measurements indicates that, perhaps not surprisingly, all the high lubricity measurements fall within the reproducibility limit, indicating that once the initial wear has taken place, further cycles result in very limited additional wear. With the low lubricity sample, the average measurements for 90,000, 135,000, 180,000 and 225,000 cycles all fall within the reproducibility limit. It would appear that an acceptable result can be achieved within the limits of the standard, running the tests at any frequency from 20 to 50 Hz, and that the choice of frequency and number of cycles is pretty much arbitrary. However, in practice what it demonstrates is a transition from a severe wear process to a mild wear process after perhaps as little as 10,000 cycles, after which the test continues to run on what is an already heavily worn or deformed surface. This perhaps provides one of the best explanations as to why sliding Hertzian point contacts are poor models of the typically mild wear processes associated with real engineering systems. Sliding Hertzian point contact tests are relatively insensitive to increased additive concentration once a complete coherent additive film has been formed. Although the tests may generate a marked difference in wear scale size between nominally good and nominally bad samples, the test usually lacks the necessary sensitivity to distinguish between good candidate samples with differing concentrations of additives. In essence, too small an area of material is being sampled compared with the available additives in the lubricant sample. Professor Malcolm Fox explains this more scientifically. The downward sweep of disparate sigmoidal curves for the friction reduction effects of different additives becomes close to one downward sigmoidal curve on a molar concentration basis. There are only a finite number of absorption sites for additives to latch onto or to adhere to, applying the Langmuir adsorption theory. Although it's a widely used test configuration, there are serious limitations with the sliding Hertzian point contact test geometry. These can be summarized as follows. It is not a model of any real engineering contact. Tests invariably start with potential failure of the surfaces. The wear transition at the start of the test is usually from severe to mild. Contact pressures change significantly during the test. It requires wear scars to be measured on 2 orthogonal axes. Wear scars can frequently be somewhat indeterminate. and it's not very sensitive to lubricant additive concentration. So how does a sliding Hertzian line contact compare with a sliding Hertzian point contact? Firstly, there are real engineering contacts that involve sliding, but more commonly sliding rolling, line contacts. Providing sensible running in sequences are used, the risk of precipitating failure at the very start of the test can be minimized. Contact pressures still change during the test, but much less and with more predictable pressure distributions than with a point contact. Wear on the counterface surface, depending on stroke length, hence overlap parameter, can be more uniformly distributed. Although it will take a longer time to generate a wear scar, simple geometrical wear scar measurement on the cylinder specimen requires just one measurement in the direction of sliding. The contact geometry is more sensitive to lubricant additive concentration because a larger amount of surface is being sampled. The following examples, comparing fuel lubricity tests run with point and line contact geometries, courtesy of Southwest Research Institute, illustrates the improved sensitivity of the latter over the former. To illustrate how much more information can be acquired from a sliding line contact test at sensible overlap parameters as opposed to sliding Hertzian point contact tests, consider the following examples. These two tests use the same specimens, running in process, test load, reciprocating frequency, and stroke, which was 25 millimeters. This allows good differentiation between wear patterns at different stroke positions. The first test sequence involved a simple temperature ramp, the nominal aim of which was to precipitate scuffing failure. The second test was run at steady set point temperature, but followed a stop-start sequence. Examination of the temperature ramp plate specimen shows accumulation of compacted fine debris at the stroke end, with debris filling the grinding marks. Away from the stroke end, shiny areas indicate material removal. Away from the stroke end, at about 25% of the stroke length, and under high magnification, there is a mixture of smearing of material in the grinding marks on the left and light abrasion on the right. Turning to the moving specimen, what is observed is not a wear scar, but an agglomeration of transferred fine debris material across the width of the contact. This is more consistent with fine two-body abrasive wear than adhesive wear. Mild two-body abrasive wear, as a result of specimen material hardness and roughness, leads to accumulation of material on the moving specimen, as well as at the end of the stroke on the plate specimen. Although this may eventually lead to seizure between the transferred material on the moving specimen and the source of the transferred material, the fixed plate, this is not an example of an adhesive wear mechanism. So we can summarize the process in this experiment as follows. Mild abrasive wear, agglomeration of fine debris on the leading edge of the moving specimen, adhesion of transferred material to the moving specimen, like-on-like materials in contact, which may eventually lead to seizure. In this case, despite the alleged aim of the experiment, we do not have a scuffing test. Instead of running at constant reciprocating frequency, a stop-start cycle is used, with each cycle resulting in a temperature excursion. During each stop phase, the temperature of the specimens is allowed to cool to a base temperature set point. Examination of the samples shows different wear behaviour. At the stroke end, on the plate specimen, we observe material pull-out with corresponding material transfer to the surface of the moving specimen. Unlike with the temperature ramp test, where debris accumulates at stroke end, with the stop-start test, we see removal of material at the stroke end, the white areas, and less wear as we move away from the stroke end. The stop-start process spreads wear zones further along the contact. Not surprisingly, adhesion of a pulled out and transferred particle to the moving specimen frequently results in an observable groove in the fixed plate specimen. So, for the stop-start test, the process is as follows. We have minimum lubricant entrainment at the start of the stroke. We have surface propagated fatigue at the asperities, and we have adhesive pull-out. This is the onset of adhesive wear. In other words, we have a scuffing test. It is apparent that the two test procedures produce very different wear mechanisms. The temperature ramp test appears to produce what one might term a false adhesive wear process. The stop-start test, with the temperature gradient the right way round and cyclic frictional energy input, produces adhesive wear as typically illustrated in most textbooks. If we consider scuffing to be either the onset of adhesive wear or at very least some form of adhesive wear process, we should at least use tests that, on examination, actually produce adhesive wear and not some other mechanism. A key justification for running stop-start type tests is that this is what happens in many real systems. The contact conditions move up and down the Strybek curve depending on the system operating point. Furthermore, in real systems, simply changing the operating point can trigger a short-term change in wear rate. This is nicely illustrated in the engine test example here from Southwest Research Institute, in which radioactive tracer technology is used to monitor real-time wear of components. One of the key issues with a simple line contact specimen arrangement is how to mitigate the geometric stress concentration at either end of a cylindrical specimen of finite width. One solution is to use a roller with a logarithmic end profile. Another solution is to use a plate specimen with curved edges and a cylindrical specimen that is wider than the plate. This then allows the possibility of using plate specimens with non-parallel sides, such that the contact pressure varies with the stroke position for a given load. It transpires that in terms of RMS and instantaneous friction and contact resistance, with a fully formulated lubricant and these samples, there is minimal difference between the frictional response of the parallel-sided and wedge-shaped specimens. The frictional response appears to be independent of contact width. Visual inspection of the samples indicates that, with a fully formulated lubricant, the wedge specimens scuff at the narrow end. With the parallel sample, a narrow band of adhesive wear is observed, covering the whole stroke length. With the parallel sample, both reversal positions indicate severe adhesive wear, characterized by deep holes in the surface. The lighter regions outside these areas have cracks in the surface, suggesting mild adhesive wear. There is a clear distinction between the severe band and the areas subjected to mild adhesive wear. With the wedge sample, the wide end reversal position indicates mild adhesive wear, with characteristic directionality. The narrow end is subjected to severe adhesive wear, with destruction of the oxide or additive protective film and plastic deformation. Comparison between the different wear regimes is thus as indicated in the slide. Axial surface profilometry shows that with the parallel samples, wear is a maximum at the stroke ends and a minimum at mid-stroke. With the wedge specimen, in comparison with the parallel specimen, the overall wear is much greater and is indeed greater at the narrow end of the wedge, as one would expect. So to summarise, the stroke ends. With the parallel, the wear is the same at each end. With the wedge, the wear is the same as the wide end, but approximately double at the narrow end, where contact pressure is approximately double. With parallel, contact pressure is constant with stroke. With wedge, contact pressure is ramping up in one direction and down in the other. The question is, does this action prevent the establishment of a stable lubrication regime, hence contributing to greater wear at the mid-stroke position? Repeatability with curved edge plate specimens and overlapping pin samples appears to be good, compared with tests where the contact width is less than the plate width. This suggests that in the latter case, variable edge effects may have an important influence on repeatability. Provided that the wear mechanism is the same at either end of a wedge specimen, the friction is independent of nominal contact area. Time-smooth friction provides little information with regard to wear transitions under mild regimes. However, changes in instantaneous contact resistance is a good indicator of wear transitions. With a curved edge wedge specimen, it is possible to generate different wear regimes at either end of the specimen, hence provide much more information from a single test run. It is possible to produce mild and severe adhesive wear while running under conditions of steady load and temperature. In other words, without resorting to the application of either ramped loads or temperatures. Now let's move on to sliding rolling line contacts and use as our example an attempt to model an Involute gear with a two-roller machine. One of the most commonly occurring misapprehensions is to assume wrongly that the pitch line velocity of actual gears to be modelled is the same as the surface sliding speed of the rollers in a two-roller machine test model. The pitch line velocity determines the contact time for gear teeth pairs. However, the rolling and sliding velocities between the gear tooth pairs depend on the gear tooth profile plus the contact time. It is these velocities that should be modelled in any two-roller experiment. With Involute gears, we have two contacting surfaces with variable curvature moving together with a complex combination of rolling and sliding. An added complication is that, away from the pitch point, there is load sharing between overlapping pairs of teeth, adding the uncertainty of dynamic loading to an already complex system. This example is based on Involute gears with a 20-degree pressure angle. Shortly after engagement, the surface of the driving gear is moving with a small velocity relative to the point of contact, whereas the driven gear has a much higher velocity. These are defined as the rolling velocities of the two surfaces. The sliding velocity of the driven tooth across the surface of the driving gear is in the same direction as the rolling velocities, and is conventionally described as a negative sliding velocity. At the pitch point, the rolling velocities are equal and there is no sliding. As the point of contact nears the end of the contact path, the driving gear is moving faster than the driven gear relative to the point of contact. The sliding velocity of the driven tooth across the surface of the driving tooth is in the opposite direction to the rolling velocities, and this is conventionally described as positive. Note that in the case of the driving gear, sliding is always away from the pitch point. This imposes a tension in the surface layers and is the reason for the observed greater tendency of the driving gear to pit in the region of the pitch point. Conditions for the driven gear are the mirror image of those of the driving gear, with sliding always towards the pitch point, imposing compressive forces to the surface layers, thus discouraging pitting. To take our analysis further, we need to introduce some definitions. With gears, the relationship between rolling and sliding velocity requires careful definition. Merit defines the rolling velocity ratio, RVR, as the ratio of the smaller to the larger velocity of the two surfaces relative to the point of contact, taking algebraic sign into account. For pure rolling without sliding, RVR equals 1, and for pure sliding, RVR equals 0. The sliding velocity ratio, SVR, is defined as shown. For pure rolling without sliding, SVR equals 0, and for pure sliding, SVR equals 1. The energy pulse is the product of the friction power intensity, the FBI, and the contact transit time. The EP, therefore, takes into account the length of time during which the material is subjected to energy input during its transit of the contact zone. The energy pulse is analogous to the Archer-Ware law. However, the energy pulse equation uses the friction force rather than the applied load. This is perhaps more logical as it takes into account the work done in the contact. Each energy pulse can be regarded as an incremental contribution to wear or surface damage in the contact, and the sum of the energy pulses can be used as a measure of the total wear. Correct analysis of the energy pulse in the real contact and subsequent modelling in the experimental design significantly enhances the chances of achieving a satisfactory emulation of sliding and combined sliding and rolling contacts. It is important to note that in many machine components there can be very high FPIs, but because the contact durations are short, the energy pulse is low and hence the incremental damage is low. We can now examine how the SVR, the RVR and the EP vary at different locations on the gear tooth. The following schematics are based on two 30-tooth gears with a 20-degree pressure angle. Note that in these sketches the SVR, which has a negative value, is here plotted as positive so that it appears above the x-axis. As the EP is a function of load, it is clear that the EP for a single tooth contact will not only vary with relative sliding velocity, but also as a result of dynamic loading and the sharing of load between successive pairs of teeth. The EP is 0 at the pitch point, despite the load potentially being at a maximum, and that is because the SVR is 0. The EP increases in the direction of the root and the tip as the SVR increases. Zero EP at the pitch point provides the mechanism for generating micropitting. High EP at the tooth tip produces conditions conducive to scuffing. It will be apparent that there are significant differences between a pair of dynamically loaded Involute gears and a conventional two-roller machine test geometry. These are summarized in the table. There is, however, one parameter that, for gears, is fully deterministic, but for two-roller machines is less certain. With gears, the points of contact between pairs of teeth, plus which teeth pairs are engaged each cycle, is determined by the design of the gears and the number of teeth on each gear wheel. With a two-roller machine, especially where surface speeds are independently controlled, the relationship between corresponding points on each roller is continuously variable. The parameters affecting performance of both gear and two-roller contacts are as follows: contact pressure, lubricant film thickness, frequency of encounter, friction power intensity, and energy pulse. All these parameters are easy to define for the two-roller contact, but less so for the gear tooth contact. However, it is clearly necessary that if we wish to model the complex operating conditions in a gear contact with a simplified steady-state model in a two-roller machine, we must start by evaluating the conditions in the former. Because of the general complexity and uncertainty, significant assumptions are inevitable. Whereas the contact pressure is relatively straightforward to calculate at the gear pitch point, the uncertainty caused by load sharing combined with varying tooth curvature renders simple and easy calculation of contact pressure elsewhere more or less impossible. With regard to lubricant film thickness, at the pitch point we can readily estimate it using any of the established Elasto-hydrodynamic film thickness calculations, for example the Dowson-Higginson equation. There is, however, a significant caveat. The calculations all assume a fully flooded inlet in the contact and minimal side leakage. In practice, most gears run under conditions of starved lubrication, and there is always side leakage. Estimating the lubricant film thickness away from the pitch point clearly requires calculation to be performed taking into account local contact pressures and local entrainment conditions. Once again, that is not easy. Gear tooth contacts are intermittent, of course. In other words, a given pair of gear teeth is subjected to a brief period of engagement, followed by a longer period rotating out of contact before once again coming into contact. The period out of contact allows time for dissipation of frictional heat and for the lubricant additive chemistry to react. It is well known that in gears running at very high speeds, the frequency of encounter can be too short to allow the chemistry to work, resulting in scuffing. The FPI and EP clearly have no meaning at the pitch point and thus need to be calculated taking into account local contact pressure, hence local load, and local sliding velocity. This is, of course, by no means easy. Hence, a simple benchmark estimate is to use the Hertzian contact pressure at the pitch point and the mean sliding velocity across the contact. This should provide basic order of magnitude values on which to base your experiment. Now to some practical choices. It is important to state that there are no established and proven test configurations or test parameters for modelling gear contacts in a two-roller machine. Hence, there's no proven right or wrong answer. However, experiments based on sensible estimates and rational choices are likely to be more meaningful than randomly chosen test parameters. First, let's consider the roller sizes. The contact between involute gears at the pitch point can be modelled as cylinders of the same local contact radius as the gears. Using rollers of equal radius to the gear radii at the pitch point is a choice made by numerous experimenters. It would seem a rational choice if one wished to perform experiments modelling conditions at the pitch point. It would seem a somewhat arbitrary choice if one were intent on modelling conditions away from the pitch point. In practice, however, roller contacts are essentially scalable, so choosing roller diameters that conveniently provide contact radii somewhere within the range of radii of the gear tooth profiles would seem acceptable. To determine the required capacity of a two-roller machine to perform our experiment, we need to carry out a number of calculations to match the machine capacity to the gear tooth contact speeds and pressures. Having first chosen the size of roller to be used, we need to perform the necessary speed RPM calculations, the load and contact pressure calculations, and the machine torque and power calculations. Typical machine torque and power calculations are as shown in the table, and this is for a 70mm diameter roller pair with 10mm wide contact width and 2000 megapascals contact pressure, and also using moderately realistic surface speeds. If you perform these sorts of calculation, you will discover how easy it is to end up specifying an absolutely enormous high power capacity two-roller machine. So having done these sums, it is sensible to review the FPI to confirm that the frictional energy dissipation in the small contacts in our two-roller machine are going to be sensible, and also, of course, to check that if we wish to be running under boundary or mixed lubrication, the nominal lubricant film thickness is appropriate. On the subject of lubrication, the normal practice with two-roller tests is to jet test lubricant into the in-running side of the roller contacts. To model starved lubrication, jetting lubricant against the outrunning side of the contact may be worth considering. Micro-pitting tests should be run at high contact pressures equivalent to those at or near the gear pitch point, but with low sliding velocities, hence low frictional energy input. Note that two-roller tests have shown that negative sliding is more conducive to pitting than sliding in a positive direction. The level of asperity engagement can be varied by varying the lubricant entrainment velocity, varying the lubricant inlet temperature, hence viscosity. Scuffing tests should be run at lower contact pressures equivalent to those at or near the gear tip, but with higher sliding velocities, hence higher frictional energy input. Typical sliding speeds are between 5 and 20 meters per second. As scuffing is a wear transition, the onset of adhesive wear, tests sensibly involve increasing the severity of conditions within the contact with the aim of precipitating the transition, but preferably not causing catastrophic failure. There are various mechanisms for precipitating scuffing in two-roller machines. Firstly, what about progressively increasing the load? As the EHD film thickness is only weakly dependent on load, the main effect of increasing load is thus to increase the frictional energy input, hence contact temperature. We can progressively reduce the lubricant film thickness, and there are two methods for achieving this. Firstly, by increasing the lubricant inlet temperature, hence reducing the lubricant viscosity, and secondly, by reducing the lubricant entrainment velocity. Finally, we can precipitate scuffing by progressively increasing the frictional energy input, and this is best achieved by increasing the sliding velocity in the contact while limiting the entrainment velocity. The need for satisfactory running in of gears is well understood. There is a similar requirement to run in test rollers. This is best performed at modest loads and low sliding velocities. Running in performs two functions. Firstly, generating plastic shakedown, which is the process of initial plastic deformation of the subsurface, and secondly, flattening the peaks of the surface asperities. Shakedown imparts residual stresses to the subsurface material, after which the contact should be elastic. This is analogous to a controlled work hardening process. The tips of the surface asperities are flattened by a combination of plastic deformation and mild wear. Increasing the sliding velocity during running in alters the shakedown behavior and increases the risk of scuffing at the asperity tips. An alternative to the steady-state slide-roll ratio behavior achievable with a two-roller machine, a variable slide-roll ratio contact can be generated by imposing a degree of rotation on a test roller, as it is reciprocated against a flat plate. In this device, a crowned or flat roller is reciprocated with a linkage connected to the side of the roller opposite the tribo contact. As the roller is reciprocated, the RVR changes with stroke position, with the RVR equal to 1 pure rolling at the mid-stroke position, and the RVR less than 1 rolling and sliding away from the mid-stroke position. Hence, the point of contact moves on both the surfaces of the roller and the surface of the plate, with a motion similar to a pair of gear teeth rolling backwards and forwards on either side of the pitch point. By changing the linkage position, the range of RVRs can be changed. The device has not been extensively used for micropitting tests, but has been successfully used as a scuffing screening test for gear oils. In this case, scuffing is precipitated in a controlled way, not by increasing the frictional energy input, but by increasing the contact temperature by electrically heating the plate specimen. Another important sliding rolling line contact is that between a cam and a follower. I have covered the simplified analysis of a cam follower contact in another lecture on lubricated friction measurement. The key wear issue with cams and followers is the contact at the cam nose, where a combination of poor entrainment conditions and high peak loads can give rise to scuffing, in other words, the onset of adhesive wear. Under these conditions, additive protection is essential. In this example, we have a quite complicated wedge-on-sphere geometry designed to promote rotation of the bucket follower, thus producing a circular wear track. For our benchmark calculations, we use a simplified geometry comprising a cylinder on flat with a 10mm wide contact width. Only by doing the appropriate analysis can we establish the lubrication regime under which our component is running, hence determine the test conditions in an appropriate model system in which to generate relevant and meaningful wear or failure data. Now let's move on to lubricated area contacts. With simple area contacts, lubricant entrainment conditions are poorly defined. Furthermore, in the absence of some form of converging geometry, it is impossible to generate hydrodynamic separation of the surfaces. It follows that, in real applications, components usually have to be designed to enable lubricant entrainment. This frequently leads to a reliance on component-based tests, particularly in the case of wet clutches, their materials and associated ATFs, face seals, and lubricated journal and plane thrust bearings. In these cases, the tribological response depends not just on lubricant and material properties, but importantly on the design of the components. In many other lubricated area contacts, the nature of the application is so specific and the contact conditions so complicated that simple tribometer tests are of little practical use. In order to achieve correlation between wear or failure in a laboratory model and that in the real system, it is usually necessary for the model to be very much application specific and in many cases to use components from the real systems. The examples shown here are perhaps all too specific to be included in a general talk on lubricated wear testing and perhaps need to be covered elsewhere as topics in their own right. And so to conclusions. In order to perform sensible lubricated wear tests, we must choose systems and procedures that allow tests to be performed under mixed or boundary lubrication, that model the required wear or failure mechanism of the real system, that generate wear and do not simply precipitate failure, that do not precipitate unwanted wear transitions, that are at a sensible contact pressure with contact temperatures, whether self-generated or externally applied, appropriate for the additive chemistry, that limit or control the frictional energy input, that have cyclic energy input, including stop-starts, if necessary, that do not attempt to accelerate the wear simply by increasing the sliding velocity or the load. On the subject of sliding Hertzian point contact tests, it's important to note that these are essentially pass-fail tests suitable for quality control applications. Repeatability frequently depends on having highly finished and highly controlled test specimen surfaces in order to maximize the number of asperities supporting the applied load at the start of the test. It's nearly impossible to avoid plastic flow at the start of the test, either on or below the surface, and it's also very difficult to avoid obliterating test surfaces. Because of the small contact scale, the number of available active metal sites is very limited, making tests rather insensitive to additive concentration. The rate and range of fall in contact pressure at the beginning of the test produces an almost digital response. Of course, most standard tests use material pairs that are unrepresentative of material pairs in real sliding application contacts. And, of course, sliding Hertzian point contacts do not model anything in the real world. It's a matter of opinion, of course, but I reckon it's pretty much a waste of time trying to improve the sensitivity of sliding Hertzian point contact tests, or indeed to try to achieve correlation with real-life applications. Sliding Hertzian line contact tests, with care, do have the potential to model certain real-life contacts. With regard to lubricated area contacts, these frequently involve actual application components. To achieve correlation requires careful duplication of the application contact conditions, in particular when it comes to lubricant entrainment. So, why is it so important to get these things right? You are probably familiar with the classification of different test systems given in DIN 50320, showing potential steps between laboratory test and real application, and vice versa. We can usually manage to characterize frictional response relatively quickly, but it usually takes a long time to generate wear or failure in real systems. Hence, sensible wear tests are likely to take a long time. It follows that if we can miss out any of the steps between real system and simple laboratory test, the potential for saving both time and money is enormous. As tribologists, we all dream of achieving convincing correlation between a simple bench test and the real-life application, if possible, missing out all the steps in the middle. I hope you found this talk both useful and thought-provoking.